Yes, today we are going to talk about adaptation and antimicrobial resistance. My name is Awauche, and please do subscribe to my channel. So let's begin with our executive summary. Microorganisms become stronger and more resistant as more chemicals are thrown at them. Just as strong and healthy immune systems become more resilient and stronger when they are exposed to pathogens. We are busy overwhelming the immune system and making microorganisms more resistant instead of focusing on this basic truth and the genuine solution, boosting the immune system. So let's have a review of antimicrobial resistance. Globally, about 700,000 people die each year from AMR, representing about 1% of global death. It has been hypothesized that by the year 2050, 1 out of every 4 deaths in Nigeria will be central to AMR. We are ostensibly on a cusp of a post-antibiotics era. If the current trajectory of these drug-resistant microorganisms is not reversed by 2050, some 10 million people could succumb to drug-resistant disease, costing the global economy 20 trillion USD. I think your best defense is a healthy immune system. So let's talk about the true cause of AMR. It will be dissatisfaction if you don't get to know the true cause or causes of this problem. Fleming and Tellman admonished that bacteria are adaptable. If they don't die, they become stronger and resilient when exposed to our magic bullets, antibiotics. The same way the immune system becomes stronger and resilient when exposed to pathogens. To start with, antibiotics. Penicillin was first discovered in 1928 by Alexander Fleming from a common mold called Penicillium notatum. Remember, a natural material. The drug entered the market at about a decade later and redefined the way that infectious diseases were viewed. As the demand for the drug increased, the synthesis of the drug came handy. Instead of using the original materials upon which the drug was formed, scientists resorted, after studying the structural elucidation, to combinatorial chemistry and directed synthesis, which led to the massive drop in the efficacy of penicillin against the Staphylococcus aureus, in whose name the drug was developed. For instance, shortly after the massive production of the drug through combinatorial chemistry and directed synthesis in 1946, the efficacy of penicillin against Staphylococcus aureus dropped to 88%. In 1950, the efficacy dropped to 66%. In 1982, it dropped to 10%, and now it is less than 5% sensitive to Staph aureus. Can anyone hazard a guess that the total depletion in the efficacy of penicillin against Staphylococcus aureus, a consequence of overuse and misuse of antibiotics that had assumed a permanent cliché in our contemporary society today, when in reality 128,000 people die each year in America because of taking medications as prescribed? Could it be the side effect of these chemically synthesized drugs? Would it have been different if the pharmaceutical industry had not embraced the combinatorial chemistry and directed synthesizing of drugs? I leave it to you to answer. So, what is the true cause of AMR? You are going to answer it going by what you have just heard. So let's talk about adaptation. Bacteria are genetically designed to be adaptable considering their surrounding nucleic acid, proteins, and cell wall, which are capable of alteration. Some alterations are temporary or reversible provided there is no buildup of the insults. However, alterations can equally be irreversible if there is a sustained buildup of the insult, which can even be transferred from one microbes to another. So let's talk about bacteria resistance. Bacteria can resist antibiotics through two ways. One is intrinsic resistance, and then the other is called acquired resistance. So, intrinsic resistance refers to bacteria's resistance to antibiotics as a result of their intrinsic or innate characteristics. Antibiotics that target bacterial cell walls, for example, will not impact bacteria without cell wall. So, all the gram-negative microorganisms or microorganisms without cell wall will not be susceptible to antibiotics that target cell wall. So that is an innate characteristic. It is an intrinsic characteristic. So when a bacterium that was previously sensitive to an antibiotic develops resistance, it is known as acquired resistance. And that is what I think we are battling today. So we talk about transfer of antibiotic resistance. So these resistant genes can be transferred from one bacterial cell to the next through three different ways. One is conjugation. When you hear of conjugation, your mind should go to sex. Bacteria are highly promiscuous. Yes, they do have sex, and they do that through conjugation. So two bacteria can pair up and link through cell membrane structures, allowing them to transmit DNA from one bacterial cell to the next. The other method is called transduction. Bacteriophage, they are viruses, or bacteriophages are viruses that infect bacteria. So genes picked up during infections of one bacterium can sometimes be carried by these viruses. These genes might subsequently be integrated into the new bacterial host DNA. The last is called transformation, and some bacteria can directly absorb DNA fragments from the surrounding environment. Yes, they can go to a burial ground, where there is an onslaught of antibiotics against bacteria. So those that may survive the onslaught may pick up the genes from the dead bacteria, so they can begin to do in addition to what the dead bacteria was previously or was unable to do. So another way in which antibiotic resistant genes can be transferred. So let's talk about antibiotic resistance mechanisms. So the bacteria will not sit idly and watch the antibiotics have a devastating effect on them. They can develop mechanisms that will evade the presence of these antibiotics. And one of the ways in which they can do that is by reducing the concentrations of these antibiotics to the targets. Yes, so bacteria can devise a way that, 10 micrograms of the active ingredient in a particular antibiotic is required to destroy a bacterium. So knowing that, the bacterium can devise a way to reduce the concentration, maybe to about 5, or maybe to about 7, or maybe to about 2, so that the concentration will not have an effect on them. And one of the ways is by developing a pump, an active drug efflux. The bacteria can develop a pump on the cell wall or the cell membrane, so that as the antibiotics enters the cell, the pump will push the antibiotics out. So by so doing, 100% of the active ingredients may not enter the cell. By developing the pump, the bacteria can reduce the concentrations of the antibiotics that will enter the cell, thereby having no effect on them. So another way is by decreasing permeability of the membrane that surrounds the bacterial cell. So the membrane can be decreased so that there will be a reduction of the concentration of the antibiotics. And the bacteria can develop enzymes. They can start producing an enzyme that will directly inactivate the antibiotics. Another way it can help, or it can help in reducing the concentrations of the antibiotics, is by modifying the antibiotics entirely. The antibiotics can be modified through mechanisms, that the mechanism that will evade the bacteria from being destroyed. So that is one way. The other way is to modify or bypass the targets that the antibiotics acts on. That pathways in which the antibiotic acts on can be modified. The target can be camouflaged. The target of the antibiotics can be camouflaged. They can change form so that the antibiotics will miss the target. Another way is by expressing alternative proteins. Like, for example, MEC-A is a resistant gene produced by Staphylococcus aureus. So MEC-A or Staphylococcus aureus can use the gene to form a penicillin binding protein, an alternative penicillin binding protein. So in a cell, you may be having two penicillin binding proteins. So once the antibiotics is affecting one, they will have an alternative penicillin binding protein that they will use. So they are evading the what? The drug. They are evading being destroyed by the antibiotics. And then the whole target can be reprogrammed. New cell wall can be produced, cell membrane can be produced, new thing can happen. So you cannot kill the microorganism. So these are some of the mechanisms that the microorganism, bacteria, can use to evade being destroyed. So what is the way forward? The way forward is by building community and boosting immunity. One of the ways that keep people alive is social interaction. Let us always have the social interaction. With the social interaction, your cellular immunity will be boosted and you will hardly fall sick. The other way is to return to the natural material, the natural way of developing antibiotics, away from the chemicals now being used. Once we return to the natural way of developing antibiotics, the antimicrobial resistance will go really low. And we can begin to think of sourcing antibiotics from the unexplored frontiers of the planet. You talk about the deep sea. You talk about the atmosphere. Yes, antibiotics can be gotten from those areas. Enough of the terrestrial environment. It's like we are terrestrial centric. So let's do less of terrestrial. Thank you very much.